Welcome to a lecture on naming and forming ionic compounds. So today what we're going to do is we're going to look at how ionic compounds are formed first, and then we're going to look at how we name those compounds. And after that, you're going to do some practice problems with some forming compounds, and then you're going to do some with naming and forming compounds. So I wanted to go through real quick with you just a little bit of review from previous lessons on valence electrons. And we did talk about valence electrons yesterday in class, but today I really wanted to talk about why they're important with our ionic compounds. Valence electrons are your electrons in the outermost shell, and they can be determined by your group number. So if I'm looking at my group number, and I want to look at valence electrons. Group number 1 has 1 valence electron. Group number 2 has 2 valence electrons. Now, this periodic table right here is numbered 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in your transition metals. But if you look at it like our other naming, we called this group 3A, group 4A, 5A, 6A, 7A, and 8A. And so what you can do with those numbers, the A group elements, is that you can see that this group has 3 valence electrons, this group has 4 valence electrons, 5 valence electrons, 6 valence electrons, 7, and then 8 valence electrons. Okay, and everyone wants to be like the noble gases. So everyone wants to fulfill the octet rule and get to that 8 valence electron, that one main stable place. Okay, hydrogen and helium are going to work towards 2 because that's the maximum of electrons in that very first energy level. So when we look at these valence electrons, what they can tell us is they can tell us how many electrons need to be lost or gained in order for an element to behave like this group over here. Okay. One other thing here is that with valence electrons, we're not going to really worry about the transition metals right now. Okay. Not that they don't have valence electrons, but we're not going to worry about them for this lesson. So how many valence electrons does oxygen have? If I look at oxygen right here, oxygen is in group 6A. So oxygen is going to have 6 valence electrons. Nitrogen is in group 5A, so that's going to have 5 valence electrons. Magnesium is over here, Mg, that's going to end up giving you 2. Lithium is up here, that's going to give you 1 valence electron. And then finally, neon is over here, and that's going to end up giving you 8 valence electrons. So now when we look at valence electrons, everything wants to get to the octet or fulfill the octet rule. So you're going to form ionic compounds or covalent compounds in order for elements to change. The elements change to become more stable. So in an ionic compound is made up of cations, which are positively charged ions, and anions, which are negatively charged. Now, a good indicator, and it's not a perfect indicator, and that's what I really tried to teach you guys last semester, but one really good indicator is if it starts with a metal and then ends with a nonmetal, typically it is an ionic compound. Now, ionic compounds are formed from the give and take of electrons. So one element will lose electrons and one element gains electrons at the same time. Covalent compounds are going to be made up of nonmetals mostly, and they're going to share electrons either evenly or unevenly. Now, that evenly is called your nonpolar covalent bonds, and unevenly is your polar covalent bonds. So ionic versus covalent continued. So again, everything wants to attain this noble gas configuration, or your octet rule. This is called your octet rule. Okay, your noble gas configuration is everything wants to get to 8 valence electrons to become stable, with the exception of hydrogen and helium. Now, covalent compounds, they tend to have low melting points and they don't conduct electricity. Whereas ionic compounds, we call those formula units. They have a high melting point. They do not conduct electricity unless you have melted them or dissolved them in water. Then they will conduct electricity. Then finally, there was one last type of bond that we went through last semester, and that was metallic bonds. Metallic bonds are formed between metals and nonmetals. And what really it is you've got these positive ions, these positive cations are surrounded by a C or moving electrons. Look at copper. Copper is going to be an example of a metallic bond, whereas silicon dioxide, okay, or silicate is actually going to be a covalent compound. So notice metallic compound is only a metal, okay? So let's go over our writing chemical formulas. Writing chemical formulas, when the first thing that you need to remember is that all ionic compounds have to have a net charge of 0, meaning your positives and your negatives need to balance out so that everything becomes neutral. Okay, that's where you're going to hit stability. You also always have to have the lowest whole number ratio in that when you're forming your ionic compounds. So if lithium forms a positive 1 charge because it loses 1 electron, and oxygen forms a negative 2 charge by gaining 2 electrons, what's the formula? Well, it's going to be Li2O. Now, there are 2 different ways for you to look at that. You can say Li has a +1, oxygen has a -2. So then if I have 2 plus 1s and 1 -2, that's going to end up giving me an overall charge of 0. So I have Li2O. Now another another method that I taught you in class was if I take Li plus 1 and O minus 2, and I swap and drop the numbers, only the numbers. You don't ever have your charges written in your compound. So I'm going to write my 2 here, and I don't ever write my 1 there. So I end up getting Li2O. So let's try another one, calcium and oxygen. Calcium is going to form a +2 charge. Oxygen forms a -2 charge, okay? And so if I swap and drop that, I get Ca2O2, but I want my lowest whole number ratio, so I get CaO. And then I can check to make sure that my charges cancel. Now, if you're looking at this and you're wondering, how do you know that calcium forms a +2 and how do you know oxygen forms a -2? It's all based on where those elements are on the periodic table. So if you have your periodic table here, okay, everything wants to get to 8. So is it going to get to 8 from losing electrons or from gaining electrons? Now, calcium is going to be over here in group 2, okay? And oxygen is going to be over here in group 6. So oxygen, it's going to be much easier for oxygen to gain 2 electrons. That's where you get the -2. But calcium, it's going to be much easier for it to lose electrons, okay? Calcium doesn't have as high of an electron affinity as oxygen does. So calcium forms that +2 charge and oxygen forms the -2. And that's where it comes from. It comes based on the number of valence electrons and the position on the periodic table. So let's look at barium and nitrogen. Barium forms a +2 charge and nitrogen forms a -3 charge. So if I swap and drop my numbers here, I end up getting Ba3N2. So again, what I did is I swapped my 3 down next to my Ba and my 2 next to my N. Notice in my final compound, I do not have my charges written at all. And then also recognize that your charges cancel. So what if we have a ternary ionic compound? So ternary, let's think about what that ternary. This right here means that there's 3. So 3 or more elements present. Okay, that's what ternary is. So if I have copper 2 phosphate. Now in this case, I've thrown in one other thing that is unfamiliar to you. Right here I have copper 2. What the heck does that 2 mean? Well, that Roman numeral right there For your transition metals, remember I said we're not going to worry about their valence electrons? Well, because your transition metals can form different charges. So copper with a 2 Roman numeral means that it has a +2 charge, Cu +2. And then phosphate right here, this is a polyatomic ion. Polyatomic ions are what that sounds like, many atoms in one charged ion, okay? So phosphate is PO4 with a -3 charge. If I swap and drop those numbers, I have to do something about the fact that there's a PO4 because that 3- goes for the whole PO4. So when I do that, I'm going to swap my 2 outside of the parentheses because I need 2 phosphates for every 3 copper, okay? So you'll also recognize that your charges cancel. Another way to, again, look at this is you could have Cu +2, Cu +2, Cu +2, and then you have PO4 with a -3, PO4 with a -3, okay? And then that's going to end up giving you +2, +2, +2. That's going to be +6, -3, -3, -6. It's going to end up giving you 0, okay? So Roman numerals, when are they used? We use Roman numerals whenever a metal can form more than one different charge. You're going to use those for your transition metals. What do the Roman numerals mean? Well, the Roman numerals tell you what the charge is on the ion. So if I have lead 2, that's Pb with a +2 charge. Copper 1 is Cu with a +1 charge. Copper 2, we just looked at that. Copper 2 is Cu with a +2 charge. So let's look at forming these different compounds. Potassium sulfide, obviously we're not 100% sure on the naming here, and I've given you names, but basically this is the compound between potassium and sulfur. So if I look on my periodic table, I see that potassium forms a +1 charge and sulfur forms a -2 charge. So I swap and drop the numbers, but remember I don't write my 1, so I get K2S. What about magnesium oxide? Magnesium is in group 2, it forms a +2, and oxide is oxygen and it forms a -2. I swap and drop, but because I have a 2 and a 2, I go to my lowest whole number ratio, so that's going to be MgO. Okay, what about calcium chloride? Well, calcium chloride, I have Ca forms a +2 charge. Chloride, Cl, forms a -1 charge. Again, you have to have your periodic table next to you when you are doing these questions, okay? Because otherwise you have no idea what calcium forms. Calcium forms a +2 because it's in group 2 and it's going to lose 2 valence electrons to become like a noble gas. The 2 swaps down, the 1 comes down, but we do not write it. That is CaCl2. What about iron 3 chloride? Well, iron 3, again, is Fe with a +3 charge. Chloride we know is -1 because it's 1 away from the noble gases. We swap and drop our numbers. We don't write our 1 in the end, so we get FeCl3. And then finally, cobalt 2 chloride. Cobalt 2 is Co with a +2. Chloride is Cl with a -1. So I'm going to swap and drop my numbers. I get CoCl2. So let's look at naming binary compounds. So we've gone from the name or the elements or the ions to the compound. But now we're going to go from the compound to the name. Okay, so whenever you're forming any ionic compounds, you always want to list the metal first or the cation first. This is kind of that, if you go back to the analogy that I use, that the metals are more like the girls on the periodic table, the non-metals are more like the boys. Always list the ladies first, metals first. Also, you could look at it this way, that when you're reading, you read from your left to your right. So list what's on your left first, then what's on your right. okay? The cation is going to carry its name. So for example, aluminum, calcium, magnesium, unless again, it's a transition metal, which you see that below. And then the anion ends in IDE. So chloride, oxide, sulfide, phosphide, nitride, okay? So your anion is going to end in IDE. Now, with the exception of cadmium, zinc, and silver, transition metals are going to form ions with multiple charges. These are distinguished by Roman numerals. So example here, I have COI2. Well, I know I forms a -1 charge. If I need two -1s, that means that cobalt must be a 2 charge. So this is cobalt iodide. And then in this case, CS2O, well, CS is not a transition metal. That is cesium. So I'm just going to write cesium because remember, the cation carries its name. So cesium, and then oxygen becomes oxide. Okay, so let's look at some practice problems. K and Cl. K and Cl form KCl. I'm going to name it potassium chloride. What about Fe plus 3 and O minus 2? Fe plus 3, O minus 2. I'm going to swap and drop my numbers. So I'm going to end up getting Fe2O3. And I'm going to name that iron 3. So I know it's iron 3 because of this plus 3 charge. Iron 3 oxide. So this is an important list for you to stop at and to write down your polyatomic ions, just so that you're able to remember what your polyatomic ions are for your future test. Now, when you're doing these notes, I really recommend that you guys are taking notes while you're doing them, because otherwise you have nothing to reference to go back to when you are doing your homework or when you are doing quizzes or tests. So what about ternary ionic compounds? This is any ionic compound that has a metal and a nonmetal, or a cation and anion, which contains more than 2 elements. Ternary is 3 or more elements. Okay, so for example, KNO3. I know there are 3 elements, so I'm going to look at my polyatomic ion list. I'm going to see right over, I actually don't have it listed here, but NO3 with a -1 charge is called nitrate. Okay, and so I'm going to look at that, and this is going to end up being K is potassium, and then NO3 is my nitrate. Okay, so whenever you see more than 2 elements, most likely you have a polyatomic ion present. So ternary ionic compounds, again, are ionic compounds with polyatomic ions. So here are some examples. MgSO4. Well, this SO4 right here is sulfate. So then that's going to be magnesium sulfate. Right here, this is going to be sodium. Sodium is Na. And then NO3 is nitrate. Right here, you have lead, and lead's a transition element that has more than 1 charge. Because I know NO3 has a -1 charge, I need 2 -1s to balance out 1 Pb. So this is called lead 2 nitrate. And then this next one right here is silver nitrate. And I don't need to include my Roman numerals there because silver only has 1 charge, which is a +1 charge. So let's look at some more examples. Ca plus 2, NO3 with a -1. I highly suggest putting parentheses around your polyatomic ions because it's very important to show that you have 2 NO3s and not 2 Ns or 6 or 2 oxygens. So if you were to write this like this, CaNO3 2, if you wrote that like that, that's really saying that you have 32 oxygens, 1 nitrogen, and 1 calcium. That's very different from this right here, which is 1 calcium, 2 nitrogens, and 6 oxygens. So what do we call that? Well, calcium has its name, calcium nitrate. Okay, this one's a little bit harder, actually quite a bit harder. NH4 with a +1, SO4 with a -2. Remember your parentheses around your polyatomic ion. So we have NH4 SO4. So we have 2 NH4s for every 1 SO4. And what do you name that? Well, NH4 is ammonium sulfate. So how do you know if something's going to end in ide, ate, or ite? Well, the difference is, does it have a polyatomic ion or does it not have a polyatomic ion? Now, one thing that I've included in your lesson for today is I've included an ability for you to print out a naming cheat sheet. I highly recommend you doing that when you're at home. Just print it out so that you have that as a reference, and that's going to kind of give you a flow chart on how to name things. But how do you know if it's ide, ate, or ite? Well, if it ends in ide, we're talking about a monatomic ion. So ide would be like sulfur, sulfide, nitrogen, nitride. But then ite or ate indicates a polyatomic ion. So nitrate is going to be NO3 with a -1. Nitrite is NO2 with a -1. Now, I do not need you to memorize these polyatomic ions. But what I do want you to do is have some sort of reference sheet for yourself. So take down some notes, write down your polyatomic ions, or print something out from online that gives you common polyatomic ions. Okay, so let's look at some practice problems. We have NaNO3. So I know that I've got my polyatomic ion right here. That's going to end up giving you sodium is my cation, nitrate. Okay. Then this one, CuSO4. Well, SO4 is going to be sulfate, so I know that I'm ending with sulfate. Okay. But what is copper? Well, sulfate has a -2 charge, and I only need 1 copper to balance that out. So copper is going to be copper 2 sulfate. Now in this case, this one is a more basic one to name because you just have two ions. You have a binary ionic compound, okay? Binary ionic, so you have 2 elements, magnesium and sulfur becomes sulfide. Notice it's not sulfate or sulfite, and this is a very common mistake people make. If there's no oxygen there, it's not going to end in ate or ite. This next one does end with an oxygen. SO4, if you look above, is sulfate. So this is magnesium sulfate. Okay. Now this next one right here, we know that that is nitrate. And we know that this is iron, but we know iron needs to have your charge in your Roman numerals. So when you look at that, we have nitrate. Nitrate has a -1 charge. And notice I need 2 of them, 2 -1s to balance out my iron. So this must be a +2. So I write iron 2 nitrate. This next one right here, I have iron again, but I don't have a polyatomic ion. So I have a binary ionic compound. And so I know that that is chloride, okay? But I still need to figure out what my charge is on iron. So my Fe, well, let's see. My chloride has a -1 because it's in group 7. And so therefore it's going to gain 1 electron to form a stable ion. And so that's going to give it a -1 charge. So I need 3 -1s to balance out my positive values here. So this must be a Roman numeral 3, iron 3 chloride. So I hope that those notes were helpful. If you have any questions or need some help, please go ahead and reach out.